Hi everyone, today I'm gonna talk about the paper named Learning Gaussian Embedding based on Transformer for Attributed Graphs. My name is Thuy Hoang. I'm currently a PhD student at Network Science Lab, the Department of Artificial Intelligence, the Catholic University of Korea. First of all, I would say that graphs are everywhere. We can see that graphs are literal representations for many real-world data, such as in biological network, where proteins and drugs they are connected and interacting with each other for the drug discovery task. We can see that graphs in the ecological network where animals they are connecting together, and moreover we can see that in the social network where users they are collected and communicating with each other by using some social networking platforms such as Facebook or Twitter also. And moreover, in chemical network, we can see that many atoms they are connecting with each other to build the different kind of proteins in the chemical network also. So graph representation learning, the goal is to map each node into a low-dimensional space while preserving most of the network information. So it means that the graph representation learning is to arm to encode nodes so that similarity in the embedding space approximates the similarity in the original network. So uh, graph representation learning serves as the core of important for many downstream tasks. There are different kind of downstream tasks. For example, we can see that in the picture we have the graph classifications, load classification, link prediction, community detection, and graph embedding, and the graph generation also. So we can see that graph representation learning plays in an important role for many downstream tasks. Over the years, there are different kind of graph embedding models, and most of them, they aim to map individual nodes to the vector points in the latent space. For example, from the graph representations, we the model try to present each node as a real-world vector uh, point vector representations in the latent space. So we can see that the model try to learn the each node embedding as the individual vector in the latent space. For example, several models like node-to-vec models, node-to-vec model treat each node as words and using random walk sampling strategy to generate the sentences as the documents. So then they use the script gram model to learn the node embeddings. Several models based on graph neural network also they use aggregation functions to collect the information from the labels of nodes to the target nodes and learn the node embeddings also. We can see that in the graph transformer models, this is one of the state-of-the-art models. They also present each node as a vector points in the latent space. So, and then they learn everything to generate the graph level representation or node level representation. However, there are several problems when presenting each node as a individual point in the latent space. We can say that maybe bilateral, a node can belong to many different clusters. And moreover, we don't have much information maybe about the uncertainty in the latent space. We don't know how to present each node, and moreover, we can see that the interaction between the nodes could be complicated and complex. So it needs to the LAN IID problem also. For example, we can see that a node can belong to many different classes. In the picture, we can see that node color indicates the community neighbor, while nodes belong to both groups are colored by green. So the green nodes belong to the science club and sports club. Recently, there are several models to present nodes as a Gaussian distributions. It's some kind of the density-based models. However, they have some cons, and they have several disadvantages. The first is they use simple local sampling strategies, and moreover, they also use the simple model to learn graph structures. For example, we can see that the graph-to-graph models uh, they have the two layers is the deep encoder models and the Gaussian embedding models. However, in the deep encoder models, they just use the feed-forward neural network as a deep encoder module, and we can see that the input for the model for the encoder model is just a single load features. So for that reasons, in this paper, we try to embed nodes as a Gaussian distributions, allowing us to capture the uncertainty of the loss. And we propose a Gaussian embedding based on transformer layers. And we use personalized ranking formulation exploits the retro ordering of the loss, capturing the network structure at multiple scales. First, the sampling strategies. So, given a node VI and the hidden state at the layer K of the VI, so the hidden state could be presented as a SIK. So here we use the aggregation mechanisms in the convolutional graph neural network to capture the graph structure of the loss. So we employ k layers of the sampling strategy where the set n vi denotes the set of neighbors of load vi, and the function aggregation denotes an aggregation operator. It may be the mean function or the pooling function also, and the hg denotes the hidden state of the node vgs. The second layers we the second layers we use is a deep encoder. So in the deep in encoder part, we use graph transformer layers, and overall we can see that um, there are three layers in our deep encoders. The first layer is a sampling strategy that I mentioned before, and the second layer, the middle layers is the transformer. We employed an original transformer layers in the middle of the our models, and then we put the densities by representations on top of the transformer layers. So we more specifically, we decide mean and sigma as a linear and nonlinear functions from the transformer layers output to represent the densities by vectors. So we can see that for each node vi, we have the two parameters mean and sigma is the linear and nonlinear functions. Here we can see that the sigma is the activation functions. In some of the node functions, we adopt a personal ranking nodes from the graph-to-go models. So for each target node Vi, we employ a set of the energy constraints from Vi to the k-hop neighbor nodes. So we can see that there are many energy constraints uh, from the target node Vi to the node Vz on and the node Vm. So it means that the energy from the I to Z should be smaller than the energy from the I to M for every Z smaller than M in terms of the k-hop distance. And then we use the KL divergence to measure the dissimilarity between the two distributions I and Zj in the latent space. And here we can see that it is calculated by using the mu and sigma functions in the latent space. And for the planning, we try to employ and test the proposed model, our proposed models, and we evaluate the embedding quality based on specific tasks, such as link prediction and node classifications. And uh, we aim to compare existing models with our proposed models also. And last is the for the evaluation of the some several limitations and suggestions for the future research directions. So in conclusions, we have completed the proposed node embedding models based on Gaussian embeddings, and the overview studies on the existing models and the implementation direction of the proposed models has been described in details, and representing the node as a density distribution function shows the naturalness of the graph structure when the latent space is uncertain. And thank you. If you have any question, please contact me at the network station now. Thank you for watching.